Welcome to the opening of the picture language seminar this fall. We're very happy to have our distinguished speaker, Mark Freedman, here today. This is the first talk. We're not going to have meetings every Tuesday, but most Tuesdays between now and the end of term. Mike is one of the great mathematicians in the world who first worked in abstract topology and then got an interest in quantum computing and other questions connected to physics. And now he's part-time at Harvard, at Google, and lives in Santa Barbara. And we're very happy to have him. He's going to tell us about how the proof of the Kolmogorov-Arnold theorem teaches machine learning, or something like that. We're very happy to hear you talk.
Thank you, Arthur, for that lovely introduction. In the last year or so, since everyone's paid attention, which I I've talked to many people in machine learning, and it's quite often that they'll mention or express some thoughts or opinion about the Kolmogorov-Arnold theorem, but I never ran into anyone in machine learning who understood the proof. And as is very common in mathematics, the proof is much more illuminating than the statement. So I want to show you, I'll tell you what the statement is. I won't neglect that, but I also want to show you the proof. So the theorem has to do with representing functions of many variables using only functions of one variable and plus, or just most simple connective. But there's a bit of a paradoxical aspect to it. So I just want to point out that despite what Cantor would tell us, there are more functions from the square, the interval squared, to the interval, say, than functions just from the interval to the interval. So this is totally obvious to a physicist. A mathematician would say they're the same number, like cardinal arithmetic. But we all know that that's a bit bogus. I mean, the way to think about this is if you discretize the square into a lattice, then you'll have, if you take a grid of spacing 1 over n, you'll have n squared points. So the number of functions will be n. Well, we'll discretize the interval as n point. It'll be n to the n squared. In parentheses, this one. This is the number of functions.
Arthur, they show you, but not the speaker.
Oh,
They don't show the speaker.
Should we turn
The speaker is there, but it's a different participant.
I thought I pinned the speaker, but let me try again. Just hold on.
You have to pin on your own computer. You can't pin
I
wherever.
can see you and hear you, but not the speaker.
The speaker is visible under the name Jun Yang.
Yeah, that's what I mean.
Okay. Can people find the speaker under Jun? I have the speaker pinned, but it's apparently not on everybody's screen.
It's fine, I think.
Okay,
So
let's go on.
people
Yeah.
can see the board or not?
Yes.
Okay. Well, okay, so I'm just doing an obvious count that functions from the square and the interval sort of scale this way, which is much larger than functions from the interval to the interval, vastly larger. So there should be no way combinatorially to take a basket of these one variable functions and assemble them into the general two variable function. But that's exactly what neural nets attempt to do. So there must be some trickery, either can't get every function or some kind of wildness is going on. So let me state the theorem. which is surprising in view of this counting argument. And then they tell you, by the way, the version I'm going to state is a refinement. Kolmogorov-Arnold wrote their papers in 1956 and 7.
Ah,
Kolmogorov, I think he was 19 years old. But their result was refined by.
But Victor Katz didn't agree.
Sorry,
Victor Katz made a comment that
yeah, I don't.
what don't you agree with? So I'll continue.
yeah, go on.
Just raise your hand if you don't agree. So the theorem was refined by many mathematicians. Speculative was involved. Every proof that I'm going to show you is in the AMS Bolton 2021 by mathematician Morris. I'll follow fairly closely to this proof. So the statement has been refined, perhaps, and the proof, perhaps more than is necessary, made very slick. So here's the statement, and I'll first state it for the square. So so there's this 5 continuous functions. From the interval to R. Such that given a continuous function f from the square to the real line, there exists a g from R to R, also continuous. And the norm, the pointwise norm of g being less than or equal to 1/7. So that, yeah, actually, let me normalize that since I normalize g. So this continuous function,
I squared to I.
no, I think it should be, so let me just check the normalization. No, yeah, let me normalize norm of g to be 1. So norm of f to also be less than or equal to 1. So that f of xy is equal summation of I equals 1 to 5. Okay, so square root of 2 is just some irrational number. If you put any irrational number in there.
So why I don't depend on F.
No, that part is universal. So let's draw, so this is the end of the statement, but let's draw a picture of it in the language of neural nets.
So did you say the norm of G is 1 or 1/7?
Less than or equal to 7.
And that's the soup norm.
It's norm, yeah. Yeah. So think of two neurons which contain a potential, and this will be the X, and this is the Y potential. And then we have one hidden layer with 5 neurons. And then we have an output layer. And the way of diagramming this theorem is that there are 5 functions here, which are phi 1, phi 2, phi 5. And there are 5 functions here, which in principle could be 5 different functions, but this is just sort of the slickness of the refinement that I was talking about. These functions are just square root of 2 times phi I. And then the rule in these diagrams in the neural net is when inputs come in, they're added by the neuron, and then it delivers some output. And the output, according to the rules here, is just apply the function g. All these are g. And then the output here, again, we follow the same diagrammatic convention that you sum the inputs. So saying an arbitrary function of 2 variables can be represented by this nonlinear neural net with these functions just being continuous, that's the same content as this formula. Because I take the value x, I apply phi I to it, I sum it at the ith neuron, the hidden layer, with the value on y applying this similar function. That gives me the value of this neuron. And then leaving this neuron, we apply the function g to this value, and then take the sum here. So it's the same. This is the picture of that statement. So, by the way, the neural nets that you mostly read about are much deeper and wider than this. They have many layers, not just one hidden layer, but they don't typically allow general functions. These would be, it's basically a linear map from layer to layer, followed by some very simple coordinate-wise nonlinearity literature. So what this is doing is it's taking an extremely general functional form for a neural net, and then showing that you can get by with a single hidden layer. So people say, if you allow extremely nonlinear activation functions and input nonlinear functions between the layers, you can express any function with a single and rather small hidden layer. Yes.
Okay, so what is special for this phi? Do we?
Well, yeah,
Yeah.
that's the whole point of the talk. And I will say that the analogous statement is true if you replace 2 with n, 5 with 2n plus 1, square root of 2. Well, now we'll need, you see, if we have 2 is replaced with n, we won't just have 2 initial, we'll have n initial values, just find the coordinates in an n cube. So we'll have to take a sum. We'll need n linearly independent numbers over the rationals. So this just square root of 2 just is replaced by independence over q. But otherwise, the proof will be essentially the same in higher dimensions. So I won't tax your ability to do arithmetic. We'll just do the case of the square.
Is it okay if I ask a question?
Yes.
I'm not sure I missed just the question that was asked before this one, but will you tell us what the phi are?
Oh, I'll construct them, yes. That's
Okay.
That's sort of the whole point. And the answer to the parenthetical question, what's the relevance of this to ML? It's not that I think people should try to do machine learning using nets of this style necessarily. The relevance to ML actually is going to be the geometry of these special functions phi. What they do is they kind of fluff the data manifold out in a way that makes it amenable to learning, or at least to representation.
So are any of these F, G, or phi differentiable?
No, In fact, it's a theorem that they cannot be. So in other words, if you try to do this same theorem in the C1, where all the functions have continuous first derivatives, then it's a theorem proved by another student of Kolmogorov a year before, I think 1955, that you cannot represent the general C1 function. And essentially the reason is dimension counting. I began by explaining how in an intuitive way there can't possibly be enough functions for this to be true. The reason it is true is because dimension counting breaks down in the continuum. And I should have made it, I'm glad you asked me that because I wanted to make a remark about space filling curves.
So F cannot be continuous, even though,
No, F is continuous.
I'm sorry, differential, F is not.
F is not differentiable.
Is there a
No,
whole,
no, no,
is the-
no, I mean, differentiable functions are continuous, so if this happens to be differentiable, you can represent it, but that will not enable you to find a differentiable G.
Okay.
So these are not differentiable, these are not differentiable. If you try to state the entire theorem in a C1 context, it doesn't work. These have to be more wild. And
but is there some Holder exponent?
I was just gonna say, Holder. So are people familiar with space filling curves? There are continuous maps from the interval that are onto the square, which cannot be done C1. The C1 curve will be nowhere dense in the square, but the C0 curve can be, and it will have Holder exponent at half. And
Well, like Brownian motion.
Brownian motion is pretty close. I mean, it has Hausdorff dimension too. It doesn't quite fill the square. The simple formula to fill the square is coordinate decimal splitting. That is, if you take a real number and write its decimal expansion out and just take the even entries to be the x coordinate, the odd entries to be the y coordinate, that'll get you everywhere in the plane with some 2 to 1-ness because of the fact that 9999 is the same as zeros. And you can actually see its Holder half because you need 20 decimal places of accuracy in the input to get 10 decimal places in the output. And that's exactly the property that delta has to be the square of epsilon in order to control epsilon. And if you wanted to fill the cube, you'd have to split into 3 groups and it'd be Holder a third. So that gives you some flavor for the fact that to defy dimension counting, these functions have to be a bit wild. But that doesn't mean it's useless for ML because you don't have to hit the function exactly. An approximation is okay there. I should say before moving on that Kolmogorov-Arnold became famous for answering in the negative Hilbert's 13th problem. But people in algebraic geometry consider this a cheat. That Hilbert's 13th problem is alive and well, and that Hilbert only had a slip of the tongue, so to speak, or a slip of the pen when he allowed a continuous answer. So let me tell you what was motivating Hilbert. Let's see, there's this formula. See if I can get it right. Right? Okay, the quadratic formula. So it explains how a root of a polynomial moves as a function of the coefficients of the polynomial. And notice that the function is made by pretty simple operations combining functions of one variable. That is, all you do is you add or subtract things, and I guess here you multiply. Now, Hilbert said, well, multiplying isn't really much different than adding as a 2-variable function if you allow 1-variable functions. Because first you can take logs, and then you can add, and then you can exponentiate. This is probably new to a lot of people in the audience because we don't have slide rules anymore. But at one point, this would be a familiar fact. So And of course, if you've ever seen the formulas for cubic and quartic, they're similar. So, but Hilbert thought that not only would exact solutions that you can write down in closed form stop as the degree increases, but he thought that the possibility that the answer could be broken up into single variable functions combined in a very simple way, like plus and times. He thought that would also come to an end. So that's what he conjectured in the 13th problem, that there'd be no way to predict the motion of a root as a composition of one variable functions and plus. And he actually knew that the time he wrote the problem, that this was impossible if you restricted to analytic functions of one variable. And later it was proved even C1 functions won't do the job. But in the way he wrote the 13th problem, it's a continuous function. Might have just been a slip of the pen. But Arnold and Kolmogorov sneaked into that gap. Constructed their counter construction. Okay, so so what's let me just dive right into the proof. So the proof consists of a very important lemma. Whole proof really is going to be this lemma. Well, actually, let me make a definition first. So given f, as before, from the square to the real line, which we norm it up less than or equal to 1. Let's just say equal to 1. Normalize this way. We define use of f to be the subset of 5 tuples of functions. So this is phi 1 through phi 5 in continuous functions on the interval to the 5th power. So it's the possible phi's such that f minus this approximation, which is the summation such that there exists the g, such that the norm of f minus the approximation, which is summation of 1 to 5, that's what that's divided here. In absolute value is less than 7/8.
Could you read the full formula?
I just rewrote the theorem. Quite a little clear. Okay, so I won't write this out over and over again. I'll just call this the approximation. So this is sort of an approximation to this function. And it depends on coming up with a g, so that there exists a g. So in other words, people have been asking me, what do these phi's look like? And that's going to be kind of the point of the talk. But we're going to consider the set of phi's, which at least aren't terrible, that they can do some little step toward approximating the function f. And that's what this 7/8 means. I mean, if this was a good approximation to f of xy, then I expect the difference to be like 0.01 or something. But remember, f has a norm 7, norm 1. So this is a tiny step for having solved the problem. If I can get the difference between the function of norm 1 and its approximation to be less than 1, I get a little bit ahead with it. So these we should think, let me just use a word, these spies should be thought of as an embedding from from I2 into R5. Right? These 1 through 5 are the coordinates. Well, actually, it's this point of the coordinates of the embedding. At the end of the day, these spies will have to be an embedding in order to separate functions.
So once you make the first step, are you going to iterate?
Yes. Yes. I'm gonna find some nonlinear dynamic, or those guys found some nonlinear dynamic that, you know, if you can knock off 10% error each time, it should exponentially solve the problem. So that's why the whole work is going to be in this line. So well, I've only given you a definition. So the lemma is that this set of embeddings, phi sub f, is open dense. In the space of all phi's. And open is easy because, oh, well, I miswrote the condition. Should be less than, not less than or equal. I wanted an open condition here. So as long as I make this condition open, the UF will certainly be an open set, because if certain embedding phi works for f, one very close to it will also work. Because G is continuous. If the values in here change slightly, this difference will only change continuously. So openness is kind of tautological. So with dense, to verify dense, what we have to do is given, so this is the whole game, is given some, I'll just call it phi. This is a set phi 1 through phi 1 through phi. Given this, we have to, let's put a 0 superscript. What we need to do is we need to find the phi, so it's phi 1 through 5, such that it's closed. The norm is less than epsilon. Normally the difference is less than epsilon. And the second property I'll write down and then explain. Phi I is constant, rational, and distinct on red intervals. I don't have red, but I have orange. Yeah, so I'll have to tell you what red intervals are and what distinct means. So to get the ith red intervals, we take the unit interval and we subtract the set of small intervals S over open intervals, S over N, 1 over N, where S is congruent to I mod phi, and capital N is a very large integer. Which I'll choose very soon. Choose to show you how to choose it in terms of that. So what this looks like you take the real line or the interval from 0 to 1. And these red intervals are kind of like, you have small gaps of size 1 over n. Where I've removed this. So these are the red intervals. That's the connected components of everything left over. And typically they'll be of length 4 over n. Typically, but if the edge cases, they might be cut off, they might be shorter. And then we refer to this subscript red intervals each. This Morris calls this the rank of the interval, and that's there are 5 ranks because the value of I mod 5 varies. So this is like one set of red intervals, but another rank would be the same picture but slightly shifted like this. So these intervals get shifted in some way. So every point in the interval is in at least 4 of these. And what did I mean when I said this function phi? So we have some function, say phi 1, 0, and it's some function like this, and we're approximating it by phi I, and on the intervals of rank I, wherever they are, the function has to be constant. That's what it says. Constant, rational, and distinct. So it's taking, we'll get some kind of approximation of the function where it's, it looks a bit like a canter, well, yeah, but it looks a bit different because we're trying to approximate phi 0 with phi with a function that has these constant steps. That'll of course require n to be pretty large to get a good approximation. And then the values, the heights of these flat spaces, those are supposed to be rational function values. And the word distinct means that phi I on the red interval, the pth red interval, is not equal to, say, phi j on its qth red interval, unless they're the same rank and the p equals q. So unless the pair IP equals IQ or JQ. So in other words, you should just think of these heights of the flat spaces as being kind of random, the random rationals. And we have to have these red intervals short, so n has to be large to get a good approximation. Maybe the last geometric concept I need to introduce is the notion of a red rectangle. Red rectangle of rank I is just simply the Cartesian product of 2 red intervals of rank I. They're mostly squares. They're mostly squares of size n over 4 over n. 4 over n. So as I said, there are some exceptional cases. So in the unit square will be tiled by, for each rank, like a large fraction of the area is covered by these small rectangles. Actually, it's like shingles on a roof, because shingles, when you buy them and put them on, they have a little gap in between. It's perfect. That's your 1 over n. But the rain doesn't get in because there are lots of terraces of the shingles. So here we have 5 terraces. And notice that if you take any point, put your finger on it in the square, there'll be at least 3 shingles over that point. Because each point in the line only misses 1 course in the x direction at most and 1 course in the y direction. So that means that, it can avoid being in most two ranks of, the rectangles, because it has to miss both x and y directions. And actually, that's why 2n+1 comes in. It turns out the key part, and you'll see this in the argument, the key ingredient to proving this lemma is that all points in the square are in more than half of the ranks of rectangles. So 3 is more than half of general. And 1 is more than half of general. Okay, so are there any questions before I define G? Okay, this is going to be an exciting moment now. We'll get our first sort of step. I think I'll go with this one.
Oh, you could start with any phi 0 and then get the phi I, is that what you're saying?
Yeah, I can't reach up to the top, but I forgot to say, I'll put it here, that norm of G also in the lemma is less than or equal to 1/7, just like in the theorem. Sorry, what was your question?
So this is the definition of this phi I for this approximation?
Yes. Yeah, so,
So it depends on phi 0, but you can take any.
well, that's the reason yeah, that's the point. So all I'm trying to prove in this lemma is that we can find phi's, which are pretty good, a little bit good, you know, that 7, 8 is good,
Yeah,
near any phi 0, because we want to show denseness of this set. So you give me the phi 0 that you think is least useful to me. And then I have to find something arbitrarily close to it with an epsilon that is a little bit useful in this problem. So you give me a kind of a challenging embedding, a list of 5 phi's, the 0 superscript. And I can show you how to find some useful phi's. And the way I do is I take this kind of weird steppy approximation of the phi you gave me. And now the key is going to be to define G. So you define G this way. You say, let's define G. So if the function f of x, y is positive throughout a red rectangle, RIR, then we set G on phi I of R I R equal to 1/7. So let me just make the notation clear. I used the letter phi for the one variable function, and just to save writing, say this is phi I. When I put the capital here, this is just now it's a function of two variables, x, y, and it's just phi of x plus third of 2 phi I of y. So I've defined my phi's in this steppy way near the phi 0 that you handed me. That gives me the capital phi, which is the result of the that's the value at the middle level of the neural net, where I combine phi of x with square root of 2 times phi of y. That gives me this value, capital I, and we're saying that if the function we're trying to get at, we're trying to approximate f, if it happens to be positive throughout this little box, this red rectangle, then we're gonna say this G, the outer function G should be a 7. Why a 7? Well, we're gonna add 5 of these things up and try to get close to f. So maybe this isn't a terrible guess. We're getting roughly a half if we add 5 sevenths together. It's somehow reflecting the positivity. And similarly, if this is less than 0 on this rectangle, then we'll set G equal to minus a 7. And to finish the definition of G, just extend G elsewhere. In a PL piecewise linear convex fashion. So in other words, remember G is a one variable function, and there are these certain values, these capital phi values, where I've defined G either to be plus or minus a 7. And then I haven't defined it elsewhere because I just have a finite number of these red rectangles. So I have a finite number of these phi values on the red rectangles, and that's where G is plus or minus a 7. So remember, G is supposed to have norm less than or equal to 7. So I just extend it like this. That's my definition of G. Okay, but now, now we're in a position to finish the proof here. I'm going to get you very simple check.
So at this point, you could have, if you wanted to, smoothly extend the function, but the issue is eventually when you take the limit, you'll run into a
Yeah.
okay.
Category theorem in a moment to piece together all these phi's, and that will bring on wildness even if it's smooth at this stage. So okay, so now let's just check. Let's just check how far fxy is from the approximation. And there are 3 cases I want to check. I want to check that we're at a point xy where this value is larger than a 7. Second case will be f of xy less than a 7. And the last case will be the norm of f of xy is less than or equal to 7. So let's look at the first case first. Suppose we consider f minus the approximation. I want the absolute value. Then I claim this is less than the largest value f can be, which is 1, since it's norm 1. And then because f of xy is at least a 7th, then if I look at a red rectangle that contains it, I want to say that it still at different places in the red rectangle, even though it might be a little less than a 7th, but it's still positive. Now, how can I justify that? Well, I never told you how I was going to choose capital N, but this is where I choose capital N. I don't choose capital N until I see F. And this is legitimate because I define, I'm looking at U of F, U depending on F. So I use uniform continuity. By uniform continuity to some size scale where the function can't change by more than the convenient number is 150, 1/56. We'll see that coming in a second. Let's just assume N is so large that the function value on any one of these red rectangles, the f function value can't change by more than 1/56. So in particular, it stays positive since it's the 7th somewhere. And then the approximation will take away 3/7. Because the three tiles, the three eyes. Remember I said every point is in at least three tiles in three different courses. In the definition of G, when it's positive on the rectangle, it's +7, so you'll lose 3/7. And then the other rectangles that you're not in, you don't know what happened, so take the worst case thing, you add 7s. And this is equal to 6/7, which is less than 7/8. So that looks good. Suppose we take F minus the approximation and try to estimate it in the other direction. Well, it's larger than 1/7 minus 1/56. And then all the counter terms from the approximation, let's assume they're unfavorable. So it could be as much, we could lose as much as 5/7. But this turns out this is minus 4/7 minus 156. It's 30 minus 33/56, which is greater than minus 7/8. So we're okay there. So we check this case. This case, sorry, I meant to have a minus, greater than a 7, less than minus a 7. This case is exactly parallel to this, so I don't need to do it. And then the case in the middle, the norm is 1 minus. The largest could be as 1 minus plus a 56. I think F minus 3 bucks now. So the point is, if the function at the point xy was less than 7, then in norm, then the 5 terms can contribute at most an additional 5/7, because that's all G is in norm less than a 7. And again, the 156 is just the variation within the rectangle. So if it's less than a 7 at some point in the rectangle, at any other point in the rectangle, it will be less than a 7 plus a 56. And then the approximation in norm can at most increase this value by 5/7. So this kind of crazy simple strategy works. That is, and the strategy is to just pick a G which hints at hints at the correct thing, based on whether the function value on the red rectangle is positive or negative. Okay, so this proves the lemma, and Arthur already basically told us how to finish the entire proof. I won't write anything more. Maybe I'll just write the steps. Now, so to derive the theorem, which fortunately is derive the theorem from the lemma, what you do is you let V be the intersection, an infinite intersection of these UFs. And what is the infinite set? You take a dense, a countable dense family of functions in the unit ball. So remember, F is a function of norm one in function space. The unit ball is separable. So there's a countable dense set of functions approximating. And since these are all open sets, when I take a countable intersection of open sets, I get something non-empty. I get a second, second category. So this is not empty. And just take the phi's, the set of phi I, to be any element of this set. And that means this particular set of phi I, this embedding that we've chosen, will work up to the 7/8 level for any function in this dense set. But if I choose an arbitrary F, I can find an F in my set, so maybe an arbitrary F prime. I can find an Fi in my countable dense set, so that the distance, the suit norm distance between F and Fi is small. Morris writes 1/72. And then the point is, by the triangle inequality, if I just use the approximation to Fi, I have an error of 7/8. And then if I add this small discrepancy between Fi and F prime, I have a discrepancy between the approximation to Fi and F, which is accurate to 8/9. So what that means is I can, by taking this embedding, which works for a dense set of functions, I can approximate any function within 8/9. And then I have a residual error. So I have sort of 90% roughly as error. And I've gotten the approximation that I want in the theorem. They're not equal, but I've got an approximation that's at least remove 10% of the discrepancy. And then I just use additivity. These G's are added at the end. So I can just, very much like a residual network, or ResNet, I can just reapply this reasoning, not to the original function, but to the difference between the function and the approximation. And that knocks off another 10%. And I do that over and over again, and I get exponential convergence of the G to the G I want. So that took a little while, but that's the proof. I want to tell you how I feel about the proof and what I think it means. Let me pause for a moment, just in case there are questions about the proof and strategy.
Can you go over the high level idea of, again, of like how you showed a UF is dense?
Yes. So open is easy, right? Because open is just that I wrote somewhere an inequality rather than a non-strict inequality. But what does dense mean? Dense means that if you pick any point, I can find a phi near that point that works. So that was supposed to be illustrated with this picture. You hand me a phi 0. This is a graph of phi 0 I. You actually hand me 5 graphs, if you like, right? And I get this sort of steppy function approximation to it, which on all but these little gaps of 1 over n is just going to be flat, and then I fill in anything in between. So these flat spots are kind of the key to the proof, because these give directions in the 5-dimensional space where the image is constant, it's not varying. Remember, these phi's, ultimately their purpose is to give you the 5 coordinate functions on the embedding. So what it means in this graph, what that means is there's a little red rectangle in which, look, if it's a course I, the rank I, it means the ith direction is not varying in this embedding. So the embedding looks kind of blocky, like a stack of sugar cubes. It's like an irregular stack of sugar cubes where the faces of the cubes are parallel to axes. So that as you move around this embedding, there's always a majority of the 5 directions in which nothing is happening. It's kind of a blocking embedding. And that's exploited in this nonlinear argument that that we have these directions in which the embedding is not exploring.
So in that construction, it suffices to choose the average value of the function over the interval and give it a rational approximation?
The average value of f.
Yeah, on that like how did you actually, what is the value of the rational number on the interval that you choose? Is it roughly the average value of the function on that interval?
Yes, you could say that. I mean, that's not necessary, but that would be fine. The point is, all that's being used is that in the suit norm, it's a epsilon approximation. And if you take the average value, that'll work. Yeah. So.
Okay, thank you.
And then maybe a point that I should have hit is the only use of square root of 2 as an irrational number was to show that this property that all the heights were distinct. Remember, I said these rational heights should be distinct. Well, when they get combined with square root of 2 of another rational, you don't want things that were distinct before to become undistinct, and that's why it's useful that square root of 2 is irrational. If you were trying to do this numerically, you could optimize quite a bit. This is sort of this argument at its theoretical level. But let me use my remaining time to tell you how I think about this. So let's think of this map phi, capital arrow. So this means this is the embedding that we've constructed from the square into R5. And this is the thing I said looks like an irregular stack of sugar cubes. Let's pretend it's smooth for a minute and just talk about it in terms of what its Jacobian would look like at each point. And the picture is, you know, if we think of the Jacobian, it sounds like this is nonsense because the map's not smooth, but you'll see the point in just a moment. If you think of the Jacobian matrix, if I write it out as a matrix, it'll be a 5x2 matrix. And most 2 of the column, right, it acts on a oh, did I write this right?
Yeah, it should be 5x2.
Right, okay. Okay, so, the matrix might look something like this. That is, there'll be 3 of the 5 rows. This is at any point. This is the Jacobian at a point x, y. A matrix like this, what it says is that the image is only exploring 2 directions in out of the 5 in function space in R5. So if I look at the minors, there are like 10 possible minors here, and only one of the 10 possible minors, 2 by 2 minors, only one of them is non-zero. So that's like this blockiness that if you look at the a 2-plane in the image of this map, this point at xy is in 5 red rectangles, and remember the function, the embedding will be constant. Sorry, the point is in three red rectangles, so it's in 3 types of red rectangles, rank I, and those are coordinate directions. The 3 coordinate directions that are covered by red rectangles will not vary because the function 5, the embedding is constant in those coordinates. So there'll be 3 out of the 5 at every point in the square. There'll be 3 out of the 5 directions that don't vary as you move in the square infinitesimally around that point. That's why I wanted to think of this in like differentiable language. That would, if it was differentiable and you wrote the Jacobian, you'd see that you only had 1 minor. There'd only be 1 2-plane that was active. But this is like a stack of sugar cubes in free space. If you move along the surface, there's, in that case, it's 1 direction in which you're not varying. You want to move down the face of the sugar cube. And the sugar cubes are lined up with the axes. So I think what this highlights is that in ML, the notion of a minor could be important. So this is just, the high school notion of a matrix minor, right? You take a square submatrix, you take its determinant, that's a matrix minor. By the way, probably no one's thought about minors for like 30 years or 20 years in the term. It's usually not, well, the point is minors only make sense when bases have been chosen in advance. It's a basis dependent notion. So in much of mathematics, it's an irrelevant concept. But in neural networks, the basis is chosen for you. There are neurons. So you should talk about minors. And just like people talk about a matrix being sparse, meaning its entries are concentrated in a few places, what we're seeing about this universal embedding of the Kolmogorov-Arnold is that it's sparse, not as a matrix, but its Jacobian is its exterior powers of its Jacobian are sparse. That's what minors are. Minors are the entries in the exterior power, like the K by K minors are the entries in the kth exterior power of the linear map. And what we're seeing is that, and I believe it's not an accident, that the data is being displayed in a higher dimension by the phi embedding in such a way that at any point in the source, only 1 minor is active and the other minors are 0. And what this does, this helps you construct the G, the next layer map, because you have these 3 directions, 3 coordinate projections in which you can now engineer your outer function G to contribute to the approximation of F, because F is not varying in those directions. So it's a constant value, and then G can be tuned to respond to that constant value. So I think there was a lot of papers written starting in the 90s, 2000s about how Kolmogorov-Arnold is irrelevant to machine learning because these functions are so wild and they're just using the great depth of real number expansions to encode information in a way that couldn't be retrieved in practice. I think all those comments are correct, but I think they're missing the point that I think the brilliance of the KA theorem is not that it uses these wiggly functions, it's that it constructs an embedding with minor concentration. And I think concentrating minors is something we should look for natively in trained neural nets. And I also think it's something that we might add to the training process. We might try to encourage concentration and see if that accelerates learning. And we might discourage concentration and see if that interferes with learning. So let me just end with kind of a thought experiment on minors and neural nets. So let me take a different example. Just pick some arbitrary numbers. Suppose you have like 4 neurons, so it's R4. And we have some map to another layer with 3 neurons. And suppose these encode some information that have been passed on from the earlier stages of the net about lines in a picture. And then maybe these might encode something like features, like on a face. And it might not be that each neuron by itself is like recognizing one feature like a nose or a mouth, but there might be some combinations of these, so, maybe these two are about noses and these two are about mouths and this one's about ears, something like that. Well, if we look at the map between these layers, and I'll think of this map as nonlinear because even in an ordinary neural net where this is a linear map, if that's the case, then I would compose it with the rel u or whatever the nonlinearity, what coordinate wants nonlinearity is here. So I would get a map that's not necessarily linear, and then I take the Jacobian. And then I take the Jacobian and I ask whether it has this blocky structure, the sugar cube structure. So I take some exterior power. Let me, just for this simple example, take the second exterior power. So now we have a map from second exterior power of R4, second exterior power of R3. So that's this is R6, R3. So I guess I think I'm writing the matrix in the right way now. That would be this map. This would be the map on 2x2 minors. And it would what would it mean if we saw just one row have large entries, with some kind of minor concentration, and the other entries were pretty close to 0. Well, how would you interpret this? It would mean that as you vary, as you move around in this 4-dimensional space of lines, it means that of the 3 possible ways of pairing these neurons, 2 planes, 3 space, it says that 2 of them are just not interested in what you're doing. Like you're changing the geometry of these lines, you're changing the values of these points, and they're just saying blah, 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 it's the same, blah, 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 the Jacobian, nothing's moving. So, if you think of these rows as possibly features, like I said, eye, ear, mouth, or something, then it looks like these lines are describing an ear, because the ear minor is active. As you change the data of what the lines look like, it's saying, oh, I feel differently about this, and it's changed, like maybe they're smaller or something. But the fact that these are not active, that the variation is 0, I would interpret as saying it's not recognized as a feature of that type. So if minors concentrated only a single row, or even more concentrated, maybe just in the site, I think that you could, so I'll write down the term, right? So we'll call this minor concentration. And what I'd like to suggest is that minor concentration should be sort of a synonym for an opinion or a judgment gelling. So like an identification of a feature maybe, or concept. Is starting to gel. So it's like if you have a two-plane from the source, so that would be one of these columns. When you look at the differential of the two-plane into 3-space, there are 3 coordinate planes in 3-space, and a typical two-plane just moves into a superposition of those 3 possibilities. So I would say that's like not a gelled concept. It hasn't really decided if the two-plane is coming in and it's just a robust superposition of the 3 coordinate two planes, then it looks to me like the neural net is still making up its mind what's there. But if it's coming in and it's all aligned with one plane, so there's a large minor and then the rest are close to 0, that's like the abstraction that's being codified at that stage of the neural net has made a decision. You know, it's this is a no, this is a year or something like that. So I would expect that later, early stages of neural net, well, early in 2 senses. So a neural net has a front to back, as if you think of a feed forward. So when you say later, you can mean the later layers, or you can mean later times during training. And I sort of mean both. I mean the later layers and at later times. There'll be some moment where there should be a phase transition between sort of a Zen-like state at the beginning of the network and at the beginning of training, where the network has to keep an open mind because it doesn't know what it's looking at and it hasn't learned enough. And then the hyperplane should be mapping into robust superpositions to different coordinate directions because it just doesn't know yet. But then there should be a phase transition where it starts to align and a concept is being created. So there are 2 things I'd like to suggest. One is, you know, hoping to find collaborators to experiment with this, but one is to check and look at training of neural nets and see whether there's a stage where the minors sharply concentrate, and it looks very far out of what you'd say is a random amount of concentration. And then the second layer of the experiment would be to alternate ordinary training steps with gradient steps which push you in a concentrated direction or the opposite to see how that new training regimen would affect training. So if you know, if it's correct that minor concentration is associated with training, you might think, well, let's just promote minor concentration for its own sake then and see if that improves the training. Or if you move to contrary to the gradient and reduce the concentration, maybe that would slow the training. So I think that there's like a natural suite of experiments that I can imagine to see whether the geometric concept behind the universal initial map of the KA theorem is actually hinting at how learning should work in neural nets. So thank you.
Thank you, Mike, for a very inspiring lecture. We have a little time for discussion. We're late, but I'd like to have questions from the room first. Are there any comments or questions here?
Do you know what are some references where we can follow up on this proof?
Oh, yeah. I wrote his name down, Bill, right in here. So I learned the proof, from a 2021, bulletin of the AMS article by Sidney Morris.
Do you have any collaborators already on?
Yeah, possibly. I mean, I'm at this CMSA program. I've been talking to a few people there, so I'm not sure. We'll have to see how active they are.
Are there questions online?
I have a small one if I may.
Arthur?
So, yeah, can you hear me?
Yes, identify yourself.
Oh, hi, I'm Arthur. Thank you for the talk. This was exceptionally clear. So I wanted to understand, this Jacobian idea, rigorously speaking, you said that as you take this limit, this function is not differentiable, but at any stage, you could have, in some sense, forced it to be smooth by taking smooth approximations. And there, this idea of the Jacobian could be made precise. And would you see that you would get an approximation? Like roughly speaking, there will be several rows where the numbers are very, very close to zero. I'm wondering if this has been done or looked into.
Yeah, so the only place where you lose the potential smoothness is when you use the Baire category theorem to take an intersection, because what's happening there is you're considering a whole bunch of different functions, f, and these functions are actually getting wigglier and wigglier because there are differences between the original function and the smoothish approximations that you're making step by step. So the differences are actually and the G's can be oscillating faster and faster as you have more points sampled by taking a finer grid. So it's the fact that you have to take this n to infinity, that these blocks become finer and finer, and then you really end up with something that's like more Cantor-like in the limit. But I think all the interest is before you've taken the limit. And that the limit is just mathematical nicety, and once you think back away from the limit. And I wanted to mention, I meant to do it earlier, but I wanted to mention a really nice reference that people can look up. There's a paper which is, if you just type into a search engine, KAN, or maybe KAN network, you'll find a paper from spring of 2024 that I know some of the authors, Jim Halverson and Fabian Ruel, we're here at the workshop at CMSA right now. But this is a very nice idea, and what they do is they just discard linearity but keep the depth. So they just consider neural nets in the usual picture with maps in between. Now we're used to thinking of these as linear maps with a coordinate wise linearity at the end, but they've scrapped all that, motivated by KA. That's why they call it KA networks. And what they do is they just take cubic splines. So they don't take really wild functions. They don't even take all polynomials. The idea is to do something that's computationally tractable. They're a reasonable number of parameters for what they call B splines with some small number of branch points, only cubic. And then they just do back propagation and gradient descent, just like you do in a traditional deep neural network to train these. And they find against their suite of test problems that it works very well. They claim, they have certain advantages, 10, 100-fold speed ups in some cases. So I think this is like a beautiful realization of the idea that you don't have to go to these wild limits in order to extract some of the idea of the KA work. So that's kind of a hybridization between, you know, KA and deep nets. Was there more to your question that I didn't answer?
No, that was fantastic. Thank you.
Well, I think this is a good point to stop. This is a really open-ended subject, and we'll have to have you back to tell us where it goes. Thank you very much, Mike.
Thank all you guys.